Alright, so let me do the review for the second half of Chapter 4. Review more or less goes in order of the sections, so these first problems are going to be from Section 4-6. And then they'll probably end up at the end of the review with problems from 4-10. I'm pretty sure it goes in order. Whether it does or doesn't go in order, it's doesn't matter, because on the test I won't put the problems in the order of how the sections came. So first problem, because of the letters, I can't do it with my calculator, because they both have a cube root of x. I'm allowed to subtract them, and when I subtract them, the cube root of x isn't going to change, so that cube root of x is going to be in my answer. The thing that will change is the thing to the left of the cube roots, and what I have to be able to combine is 6t minus 4t. And when you're subtracting, only the numbers in front of the variables or the letters change, so 6t minus 4t is 2t. I don't need the times sign between the 2t and the cube root. The only reason I put the times sign in is so it didn't look like it was t cubed, because I want it to be cube roots of x. So the best answer to this would have a 2t times the cube root of x, and if you put a times sign in, it's completely fine, but it's not necessary. So part B, because it only has square roots and it doesn't have letters, I could do it on my calculator. So I'm going to check on my calculator. Both of the square roots are square roots that I know. The square root of 25 is equal to 5. The square root of 49 is equal to 7. So if I was not using my calculator and just using my knowledge, I don't need factor trees to do basic square roots of numbers that I know the square root of. So I can find each of the square roots first, and then just add the results. The answer to this problem is going to be 12. And again, this is a nice-ish problem because it only has square roots. It doesn't have letters, which means I can check the answer on my calculator real quickly to make sure I haven't messed up. So I'm going to go to the square root of 25 plus the square root of 49 on my calculator. If I see anything other than 12 when I hit equals, then I'm going to look for an error. But I see 12, so I feel good about my work. Part C has letters, so I can't do it on my calculator. And if I look at the radicals, the first radical has an x, the second radical has a 16x. They're both fourth roots, which is a good thing, but I can't add the terms without reducing the radicals. So I'll look at each of the radicals. The first radical, under it's just a single x, it doesn't reduce, because to reduce a radical with a fourth root, you have to have a 4 of a kind. The second radical with a 16 and an x, if I do a prime factor tree for 16, 16 equals 2 times 2 times 2 times 2. So when I go to reduce the fourth root of 16x, I'm going to get a 2 in front of the radical from the 4 2's in the prime factoring for 16. I won't get a number under that radical because there isn't a number after that thing that I boxed, the 2's that I boxed. The x under that radical is just going to remain under that radical because there's not a 4 of a kind. So this radical is going to reduce to 2 times the fourth root of x. So if I do that change, I can leave the first radical 7x times the fourth root of x. I can leave the 2x in front of the second radical, but also in front of the second radical I need to bring out a 2 and then leave the fourth root of x. Notice I didn't put the times sign between the 7x and the radical nor the 2 and the radical. It's not necessary. It just helps me when I'm writing the problems up, because my program can sometimes make exponents. It could have made this look like x to the fourth power as opposed to the fourth root of x. In the second radical, the 2x that was outside the radical and the 2 that I brought outside the radical need to be multiplied. And when you multiply those, you just multiply the 2's. So I'm still leaving the first piece alone. I'm going to change the second piece to 4x times the fourth root of x. Now, under each of the radicals, I have an x, and it's a fourth root of x. So to simplify this, I just have to add the 7x and the 4x. And when I'm adding with x's, I'm only adding the numbers to the left of the x's. The x's don't change. Similarly, when I'm adding with radicals, the part under the radical doesn't change. It just remains. So the answer to this problem, the number's going to be an 11. I'm going to have both an x and a fourth root of x. When you're adding with radicals or with letters, the radical and letter parts don't change. Only the numbers to the left of the letters change. So the best answer for part C is 11x times the fourth root of x. 14 is multiplying. First problem I could do completely on my calculator because it only has square roots and it doesn't have letters. I'm going to do it by hand the best I can, and I'll check on my calculator. So the first thing I do, if I have two square roots, I can multiply the numbers under the square root. I multiplied the 3 and the 6 and got 18. Now I'm going to do a prime factor tree for 18 to reduce that radical. 18 in its prime factoring is 2 times 3 times 3. And that tells me I need a 3 outside the radical and a 2 under the radical. So for my final answer, I'm going to reduce that square root of 18 the best it can be reduced. And the best it can be reduced is with a 3 to the left of the square root symbol and a 2 under the square root. Because in a square root, when I'm reducing, every time I have a pair, I get one of those in front of the square root. Double check this on my calculator real quickly. So I'm going to go square root of 3, square root of 6. I don't think I need the time signs between those. It's assumed that they're going to be multiplied if I don't put a symbol. If I see anything other than 3 square root of 2, I'm going to go back and check my work. But it looks right. 14b, unfortunately, I can't check so nicely because all the letters. So first thing to do is I'm going to multiply. When you multiply 2 cube roots, you get another cube root. What I have to multiply is the 4xy times the 4x squared y to the 5th. And basically I'm just multiplying the like pieces. I'm multiplying the 4's together, the x and the x squared together, the y and the y to the 5th together. The first x and the first y that don't have exponents have implied ones. So I'm going to make those exponents happen. The 4 times 4 part of this is going to be a 16. For the x's, I'm going to add the exponents and get x to the 3rd power. For the y's, I'm going to add their exponents and get y to the 6th power. Now I'm going to reduce each of the pieces. I'm going to reduce the cube root of 16. I'm going to reduce the cube root of x cubed. And I'm going to reduce the cube root of y to the 6th. To do the cube root of 16, I'm going to get a factor tree for 16. So 16 equals shift quote key. 16 is equal to 2 times 2 times 2 times 2. So the cube root of 16, it's going to reduce to have a 2 outside the radical and a 2 under the radical. So the cube root of 16 is 2 cube root of 2. And in my answer, I'm going to have a 2 to the left of the radical and a 2 under the radical. There's 2 ways to reduce the cube root of x cubed. The more efficient way is just to divide the exponent divided by the index. If you can divide the exponent by the index and you don't get a fraction, that's the quick way to reduce. The other way to reduce the cube root of x cubed is to write down 3 x's. And when I write down 3 x's, that tells me there's going to be 1 x outside the radical and nothing left for under the radical. So the x part is going to be just an x all outside the radical. For the y's, there's also 2 ways to reduce. I could divide the exponent 6 by 3 and learn that I get a y squared outside the radical and nothing under the radical. Or I can write down 6 y's in a row and make groups of 3. I get 2 groups of 3 with nothing left over. That tells me I have 2 y's outside the radical, nothing left over, so there's no y's under the radical. The 2 y's outside the radical, I'm going to multiply and make them a y squared. So the best answer to part B is 2xy squared to the left of the radical and a cube root of 2 for under the radical. Part C is another horrible multiplication problem. And it's mighty complicated. So first I have to multiply outside radicals with outsides, unders with unders, and then reduce. So outsides with outsides, I'm going to multiply 8 times negative 2a and leave those outside the radicals. And then under the radicals with under the radicals, I'm going to multiply ab times b. And whatever that multiplication simplifies to, I'm going to leave under my radical. So this isn't a foiling problem. There isn't a plus sign between the letters and the numbers to make me foil. So I'm just going to multiply outsides by outsides. This outside times outside, I can multiply the 8 and the negative 2 and get negative 16a. Under the radical, I get ab squared. Now I'm going to try to reduce under that radical. Under the radical, there's a single a and there's a b squared. The single a is going to remain under the radical because there's not a pair of a's, and in a square root I need a pair of something to get something out. The b squared is going to come outside of the radical as a single b, and there won't be any b's left under the radical because after I made my groups of b's there was nothing left. So for an answer to this problem, I already have a negative 16 and an a to the left of the radical before I reduce the radical. When I reduce the radical, I'm going to get a b outside the radical, and this a is going to be under the square root symbol or under the radical. So for an answer to part C, I'd write negative 16ab times the square root of a. Finally a problem I can use. On the next two problems I can use my calculator to check my work. It doesn't matter if I check before I do my algebra by hand or after. I'm going to do the by hand first and then check. So there's two multiplications I need to do for part D. I need to do 2 square root of 3 times 4 square root of 3 and 2 square root of 3 times negative square root of 2. Now I'm going to emphasize times negative 1 square root of 2. Even though there's not a 1 written there, I'm assuming there's a 1. The first multiplication, I'm going to multiply the 2 times 4, leave those outside the radical, and the 3 times 3 and leave them under the radical. So I'm going to get 8 square root of 9. The second multiplication, I'm going to multiply 2 times negative 1 outside the radical and 3 times 2 under the radical. The 2 times negative 1 I'm going to write as a negative 2. The 3 times 2 I'm going to write as a 6. So the multiplying gives me 8 square root of 9 minus 2 square root of 6. Anytime I have a square root, I should try to reduce it. The square root of 9 I know in my head to be 3. So I'm going to change the first piece to 8 times 3, which is 24. And then the second piece, the 6 outside under the radical, its prime factoring doesn't have any pairs, so it doesn't reduce. So in my answer, I should have two pieces, a 24 minus 2 square root of 6, a 24 and a minus 2 square root of 6. Let me double check now by going 2 square root of 3 parentheses 4 square root of 3 minus square root of 2. And I see 24 minus 2 square root of 6, which is identical to what I wrote for an answer, so I'm feeling really good about my work. I'm going to do the same thing for part E. I'm going to do it by hand first, and then I'm going to check. So E's a foiling. Firsts are 5 square root of 3 times 4 square root of 3. Outers are 5 square root of 3 times, I'm going to emphasize minus 1 square root of 2. Again, I like having that 1 there. It helps me multiply. The inners are 6 square root of 2 times 4 square root of 3. And the lasts are 6 square root of 2 times negative 1 square root of 2. Again, I threw that negative 1 there. It just makes it easier for me to do the multiplication. So now I'll finish this up. First, I multiply the 5 and the 4 and get 20. I multiply the 3's and get the square root of 9. At some point, I'm going to need to reduce this. This comes out to be 20 times 3, which is 60, because the square root of 9 is 3. For the outers, I multiply the 5 and the negative 1 and get negative 5. I multiply the 3 and the 2 and get the 6 under the square root. 6 isn't reducible, so that square root's not going to reduce. It's just going to stay negative 5 square root of 6. For the inners, I multiply the 6 and the 4. I get a positive 24. And I multiply the 2 and the 3, and I get a square root of 6. Again, the square root of 6 doesn't reduce, so I'm going to temporarily leave that 24 square root of 6. Eventually, I'm going to combine these together. My last, I multiply 6 times minus 1 and get minus 6. I multiply 2 times 2 and I get the square root of 4. I know the square root of 4 to be 2, so for the last I'm going to write negative 6 times 2, which is minus 12. To finish this problem up, I need to go 60 minus 12, which is the first and the last, and those combine to be a 48. And for the inners and outers, I just need to combine the minus 5 and the plus 24. And minus 5 plus 24 equals to 19. And I'm going to leave the square root of 6 and get a positive 19 square root of 6. So hopefully when I do this by my calculator, I get the same 48 plus 19 square root of 6. So let me double check. So initial problem is 5 square root of 3 plus 6 square root of 2 times 4 square root of 3 minus square root of, delete, get out of that radical, minus square root of 2. I think I entered it just like it looks, and obviously I didn't. Let me start over. Parentheses, 5 square root of 3 plus 6 square root of 2, parentheses, 4 square root of 3 minus square root of 2. Now I think I entered it right. Thank gosh. So I got the same 48 plus 19 square root of 6, so I feel pretty good about my answer because it matches up to what I did by hand. The next problem is dividing, and the first problem that I see, it's a friendly dividing problem. Well, it's a rationalizing a denominator, which is a dividing because it's a fraction. I'm supposed to write an equivalent fraction that doesn't have a square root in the denominator because there's only square roots and there's no letters. My calculator knows how to do this. By hand, what I would do is multiply the numerator and the denominator by just a copy of the denominator. In the numerator, I'm not allowed to multiply a number outside a square root with a number under a square root, so I just get 2 square root of 6. In the denominator, you can speed multiply and simplify all kind of in one step. When you multiply 2 identical square roots, ultimately what it's going to reduce to, it's what's under one of the square root symbols without the square root. So that's the first step, and then I'm going to simplify. This 2 and 6 will reduce. The 2 will become a 1, the 6 will become a 3. And when I do this on my calculator, the 1 that I have written in the numerator, it definitely won't show. But I think it will show these. And you can't simplify this anymore because I can't cancel something outside a radical with something under a radical. Let me double check now. So boom, 2 over square root of 6. And 2 over square root of 6 equals square root of 6 over 3. So I did perfect. 16, unfortunately, I can't use my calculator because of the x's, but I can certainly do it the same way. 16 isn't that different than 15. I'm going to multiply by an exact copy of the denominator of itself. When the denominator just has no adding or subtracting and it has a square root, the best way to reduce is to multiply by an exact copy of the denominator over itself. In the numerator, because I can't multiply something outside a square root with something under a square root, I just leave everything written next to each other. In the denominator, I'm multiplying 2 identical square roots. Ultimately, when you multiply 2 identical square roots and simplify, what you get is what's under one of the square roots without the square root symbol. So multiplying by square root of x over square root of x gives me 2x square root of x over x. The x's are going to cancel, which means I've canceled the entire denominator, so my answer doesn't need to be a fraction. What I have left in the numerator, I just need to write and make it my answer. So I'm going to write my answer as 2 times the square root of x. $17 I can do completely on my calculator because of the lack of letters, so let me try to do that quickly. I'm going to go negative 5 over 5 plus square root of 7. My goal for an answer will be either this or something that has the numerator flipped, but I think it's going to be exactly this. So that's what my goal is for an answer. The difference between the last two problems in this is the plus sign in the denominator. When that's the case, you have to multiply by the conjugate of the denominator or the denominator with its sign changed. So if I do that, I can see where the numerator is going to happen. In the numerator, I'm going to do two multiplications. I'm going to multiply negative 5 times 5 and negative 5 times negative square root of 7. When I multiply the negative 5 times 5, I get a negative 25. When I multiply the negative 5 times the negative square root of 7, I'm multiplying two negatives, so I get a positive. I can't get a 35 here because I can't multiply something outside a radical with something under a radical. So that gives me that part of my answer. And now I'll get the 18 part. The denominator, I have to FOIL. If you want to, in the denominator, you can limit yourself to doing just the first and the last because the outers and the inners are going to cancel. But I'll do them all. So firsts are 5 times 5, which is 25. Outers are 5 times minus square root of 7. Positive times negative is a negative. I leave the 5 and the 7 next to each other. I can't multiply something outside a square root with something under a square root. Inners, square root of 7 times 5. That's both positive, so I get a plus sign. I'm going to get a 5 square root of 7 for that. Last, positive square root of 7 and minus square root of 7. Positive times a negative is a negative. I want it to be slick. I would have just written 7 here, but I could write square root of 49 because that's legal to do. That's how the long way to simplify. My outers and inners are opposites, so they're going to cancel. My first of 25 and my last, that comes out to minus 7, will reduce to give me the 18. So I've verified by hand that my calculator knows what it's doing, and this is the best answer for that problem. 18, immediately when I see negatives under square roots, if I'm going to do them all the way on my calculator, I'm going to have to put my calculator in complex mode, but my calculator won't do prime factor trees in complex mode. So by hand, anytime I have a negative under a square root, I can turn that negative number positive if I pull an I out after the square root, and I'm going to reduce the square root of 50. So 50 equals shift factor tree. 50 in its prime factoring is 2 times 5 times 5. So the square root of 50 is going to reduce. We'll have a 5 outside the radical and a 2 under the radical. So there's multiple forms of the answer that are okay. My calculator will do this. It'll write a 5 outside the radical, a 2 under the radical, and then the I. But it's pretty good at making sure the radical sign doesn't extend over the I. A lot of times, because I don't write that well, I will shuffle the I and move it to the left of the radical to make it clear that it's not under the radical. Because multiplication is commutative, that's legal to do. If I wanted to do 18 on my calculator, I have to be in complex mode. So I hit the mode button, type in number 2 for complex. Now you see the CMPLX up top, so you can do square root of negative 50. So now I go square root negative 50, and my calculator gives me that version of the answer, which it's just the way it does it. I can't do prime factor trees in complex mode, but I can find square roots of negatives all day in complex mode. So if I wanted to do 19 by hand, because this is preferred, I'm going to make each of the square roots positive. I'm going to make this 2 times the square root of 18 times I minus the square root of 50 times I. Anytime I have a negative under a square root, that doesn't apply to cube roots, fourth roots, or fifth roots, just square roots, I can make the negative positive by making an I after or before the square root, just multiplied by the square root. Now I'm going to do a prime factor tree for 18. To do that, I need to put my mode out of complex. I'm going to hit mode and 1. And now the complex went away, and I can do a prime factor tree for 18. The prime factor tree for 18 is 2 times 3 times 3. So for that, I'm going to get a 3 outside the radical and a 2 under. So for the first radical, the 18, I'm going to get a 3 outside the radical and a 2 under that radical, because that's how the square root of 18 reduces. And ultimately, this is going to be 6 square root of 2 times I. second piece, I'm going to do a prime factor tree for 50. So I'm going to go 50 equals shift quote key. 50 is 2 times 5 times 5. So the square root of 50, I'm going to have a 5 in front of the radical and a 2 under the radical. So I'm going to get a 5 under the radical, a outside the radical, a 2 under the radical. Now both have i's and the radical part's the same. To simplify these, I'm just going to subtract the 6 minus 5 and get 1. And for my answer, there's a bunch of ways I can write my answer. First of all, I can include the 1, but I don't have to include the 1. Similarly, I can write the I before or after the square root. My calculator will probably, when I do it, do that for an answer, if I had to guess. It definitely won't show the 1. It finds that probably just kind of silly to show. And then it always writes the i's after the radical as opposed to before the radical. So in order to do this on my calculator, it has to be in complex mode. So I go mode 2, it's in complex mode. Now I go 2 square root of negative 18 minus square root of negative 50. And I bet I see that. And I do exactly square root of 2 times I. And very, very specifically, the I is after the radical and not under the radical. That's why, so if you did this would be wrong. If you wrote that for an answer, that's an error, because the I is outside the radical, whether it's before or after it. For 20, I can do each without my calculator pretty easily. The square root of negative 9 is going to be 3i. The square root of negative 4 is going to be 2i. And when I multiply 3i times 2i, I multiply the 3 and the 2 and get 6. I multiply the I and get I squared. Because I squared is equal to negative 1, I can change 6i squared to 6 times negative 1. And this whole thing is going to equal negative 6 for my answer. Again, I'm going to double check this to make sure I haven't messed up. I'm going to go square root of negative 9 times, square root of negative 9, get out of the square root, times square root of negative 4. And I see negative 6 perfectly. I just changed problem 21. We'll never even see the original problem 21 because I haven't liked that problem for years. So I just made up a new problem, and when you print your problem 21, we'll say that. If I wanted to do this without my calculator, I need to get the i's first. So I'm going to go, this first radical is the square root of 2 times I. The second radical is the square root of 18 times I. Now I multiply under radicals by under radicals and leave those numbers under the radical. So I'm going to multiply 2 times 18 and leave them under the radical. And I'm going to multiply I times I and leave them outside the radical. The 2 times 18 under the radical turns into a 36. The I times I turns into I squared. Square root of 36 I know to be 6. I squared I know to be negative 1. Just made another problem that had an answer of negative 6, which is fine. So let me double check this, pull out my calculator, and do square root of negative 2, and I probably don't even need the times sign, square root of negative 18. And it tells me it's negative 6, so I did perfectly well on my new problem 21. 22, my calculator should spit out the answer just nicely. I could do it by hand first or on my calculator first. I'm going to do both. So let me try 6 minus 5i, which is on the ENG key, minus parentheses 4 minus 3i, again hitting the ENG key. The answer to this is going to be 2 minus 2i. If I'm doing this by hand, I drop the first parentheses and get 6 minus 5i without doing any changing. In the second parentheses, I attach the negative to the 4, and I flip the sign on the 3i from negative to positive. So my parentheses are gone. Now I combine like terms. The like terms are the 6 minus 4, which is going to give me the 2 part of my answer, and the minus 5i plus 3i, which is going to give me the minus 2i, because I just combined the minus 5 and the plus 3, and there's exactly the answer that I came up with my calculator. I'll do the same for 23. I need to do them both by hand in my calculator. I don't know which one I'm just in the mood for doing this first. So 4 minus 3i squared. The answer to this is supposed to be 7 minus 24i. To get there by hand, because this is a binomial being squared, I'm going to write it without the exponent, and I'm going to FOIL. So firsts are going to be 4 times 4, which is 16. Outers are going to be 4 times minus 3i, which is minus 12i. Inners are minus 3i times 4, which is another minus 12i. Lasts are minus 3i times minus 3i. Negative times a negative is a positive. I multiply the 3's together and get a 9. I multiply the i's together and get I squared. So the FOILing gives me 16 minus 12i plus 9i squared. These two minus 12i's don't cancel because the 12's are both negative. They combine to give me the minus 24i. The 16 plus 9i squared can turn into 16 plus 9 times negative 1, because I squared is negative 1. So this could be 16 minus 24i, and then either plus negative 9 or minus 9. And then I do 16 minus 9 to get my 7. So the answer of 7 minus 24i, which I knew to be the right answer, isn't that hard to get without my calculator. It's just a FOILing problem in disguise. 24, same deal. I can use my calculator to check out these answers real quickly, so let me try this. So fraction, negative 3 over 5 plus 4i. My calculator does these as two fractions. It's gonna, my calculator gives me this, negative 15 over 41 plus 12 over 41i. I'm almost guaranteed when I do this by hand, my answer is going to be negative 15 plus 12i over 41, because the I in the numerator, the I to the right of that fraction could be brought into the numerator. And then you have two fractions with the same denominator. You can put the numerators next to each other, separated by that plus sign. So one of these answers is going to be absolute. They're all okay. My calculator answer is, in some sense maybe the best answer, but it's not the answer I come up with when I do it by hand normally. So to get here by hand, I have to multiply by the conjugate of the denominator, which is the denominator with the sign change. So I'm going to multiply by 5 minus 4i over 5 minus 4i, and then I'm going to do the numerator separately from the denominator. So for my answer, the numerator, I need to do two multiplications. I do negative 3 times 5 and negative 3 times negative 4i. The negative 3 times 5 is the negative 15 in my answer. The negative 3 times negative 4i, they're both negative, so I get a positive. 3 times 4 would be 12 in general. So that's part of my answer. And the denominator part of my answer, to get that number 41, I'm going to multiply 5 plus 4i times 5 minus 4i, and I'm going to FOIL. I'm going to go firsts are 5 times 5, which is 25. Outers are 5 times minus 4i, which is minus 20i. Inners, 4i times 5, which is plus 20i. And lasts, 4i times minus 4i is minus 16i squared. The outers and the inners cancel because they're opposites. And what I'm left with is the first, which is 25, And the last, which is minus 16i squared, but that I squared I can change to a negative 1. So I can change it to 25 minus 16 times negative 1. This double negative is going to go plus, and I'm going to get 25 plus 16, which is the 41 that I put in my answer. So this is the answer that I'd probably write on my key. And if you're doing it from your calculator, you should be able to take your calculator answer and put it into something that the algebra, doing it by hand, would lead you to. 25 has a problem with an equal sign. I'm going to get an answer and I'm going to check my answer. To do 25, it has a cube root. Cubing gets rid of a cube root. And if I cube one side, I have to cube the other. On 25, on the left side, cubing cancels out the cube root symbol, leaves me with the b that's under the cube root. On the right side, I just need to cube the 3 because the 3 is not negative. I don't really need a parentheses. I get 27 from it for my answer. I should always, when I solve a problem with an equal sign, check. It's not absolutely necessary, but it's not that hard. The original problem says the cube root of b equal to 3. I should be able to plug in a 27 for b and simplify. And when I do the cube root of 27 on my calculator, it tells me that when I plug my answer back into the original problem, I'm left with a true statement, and when that happens, I know my answer is correct. So the answer is 27. Checking is optional, but it's certainly not a bad idea to do. 26 has a square root, so I'm going to do something similar for 26 that I did for the last problem. Squaring gets rid of a square root. So on the left side, if you cancel out the square root symbol with the square, you're left with 2 minus 5x. And on the right side, you have 8 squared, which is 8 times 8, which is 64. Now I'm going to minus 2 from both sides and get minus 5x equals to 62. And then I'm going to divide both sides by a minus 5. On the left side, I'm left with just a positive x. On the right side, I have a fraction that doesn't reduce, that has a negative in the denominator. I'm going to move that negative up to the numerator. I think that's the correct answer for 26, but I should certainly check. Again, it's not horrible if you don't check on this problem. But for these problems, there's one style of problem, the kind that needs factoring, that if you don't check, you might write down an answer that doesn't work. So the original problem before I squared was 2 minus 5x under a square root equals to 8. I changed that x to minus 62 over 5. I put it in a parentheses just because it's negative. Now I'm going to simplify this left-hand side. I'm going to go square root of 2 minus 5 parentheses fraction negative 62 over 5. So if I see an 8, because that's what the right side is, I'll feel good about my work. If I don't see an 8, then that means I made a mistake. And since it reduces so that both sides come out to be 8, I haven't made a mistake. 27 as a fraction exponent. What I'm going to do is make the fraction exponent into a radical. X to the 1/2 power is the same as the second root of x minus 3 to the first power. If I write a 2, it means square root. If I don't write a 2 and don't write anything, it still means square root. So it's more efficient to write the problem without the 2. And an exponent of 1 you never really have to write. So I can rewrite the original problem to the square root of x minus 3 equal to 2. Generally, I always say 1/2 power is square root, 1/3 power is cube root. And now I'm going to square both sides. On the left side, the squaring will cancel out the square root symbol, leave me with the x minus 3 that's under the square root. On the right side, 2 squared is 2 times 2, which is 4. I'm going to add 3 to both sides and get what I hope to be my answer of x equal to 7. I'm done, but I should definitely check. The problem before I got started with it said x minus 3 to the 1/2 equals to 2. I should make sure that when I change the x to the number I say the answer is, that I get a true statement. So it should be the case that 7 minus 3 to the 1/2 power reduces to 2. So I'm going to go 7 minus 3 exponent fraction 1/2 power. If it says 2, I feel good about my work, and it does. (28), it's a bit of a mess because I have the square root isn't isolated. So I need to do some algebra to get the square root isolated, and that's going to take me 2 steps. I need to make the square root of 3x to be the only thing on the left side of the equation. To get it there, I'm going to start off by minusing 4 from both sides. On the left side, the 4's would cancel. On the right side, 12 minus 4 is 8. And then I'm going to divide both sides by 2. Because on the left side, the 2's outside the radical. They're cancelable. Fraction is gone. I'm left with just the 3x. On the right side, I have 8 over 2, which is 4. So I've done enough work to get the square root isolated. Now it will help. I can get rid of the radical by squaring both sides. If I squared any earlier than this, there's a reasonable chance that I would have made an algebra error and not got the right answer, or my answer wouldn't check. Now that I've done the work to isolate the square root, I square. Squaring cancels out the square root symbol, leaves me what's under the square root. To the right of the equal sign, 4 squared is 4 times 4, which is 16. And now I'm going to divide by 3. I think x equal to 16 over 3 is the answer. Anytime I get an answer to a problem that has an equal sign, I should check. Because it's effortless to check in some sense. The original problem was 2 times the square root of 3x plus 4 equals to 12. It should be the case that 2 times the square root of 3 times 16 over 3 plus 4 equals to 12. So this side has to reduce to be 12 again. For me, it's not hard to do this. So I'm going to go 2 square root 3 parentheses fraction 16 over 3 parentheses, and then get out of that to do my plus 4. So the plus 4 isn't under the square root. Only the 3 times the 16 over 3 is under my square root. If when I hit equals, I see a 12, I know my answer is right. And I did, so I know my answer is correct. So there's no reason to miss any points on a problem that has an equal sign, because it takes, I don't know, 15 to 30 seconds to check, and you should definitely have that extra time on the test. There's not that many problems that have equal signs, so you should check every one of them. The last problem on the review, if you don't check, you'll probably make a mistake and lose some points, because on this problem, I'm going to get 2 solutions, and I think only one of them is going to check. So just like any problem we had that has a square root, squaring gets rid of the square root. So for problem 29, the left-hand side, if I square it, the square root symbol will go away. I'll be left what's under the square root. The right-hand side, I have to FOIL to simplify it because I'm squaring a binomial, and that's a foiling problem. So I'm going to leave myself some room to work on the right-hand side. I'm going to FOIL. Firsts are x times x, which are x squared. Outers are x times minus 3, which is minus 3x. Inners are minus 3 times x, which is minus 3x. Lasts are minus 3 times minus 3, which is plus 9. So the right-hand side, after I FOIL it, the outers and the inners won't cancel because they have the same signs. They have to have opposite signs to cancel. Since they don't cancel, I'm going to add them and keep them negative. So now I've gotten rid of the radical. I have a problem that has a square. And generally when I have a square, I need to solve by factoring. And factoring is usually only productive when the problem is set equal to 0. So I'm going to take the time to get this problem set equal to 0 by minusing 2x and adding 3 to both sides. On the left side, when I minus 2x and add 3, I cancel the 2x and the 3 and I get a 0. On the right side, the minus 6x and minus 2x combine to be a minus 8x. The positive 9 and positive 3 give me a positive 12. The right-hand side needs to be factored, and I need double negatives. So I could do -1 and -12, -2 and -6, or -3 and -4 for my lasts on my right-hand side. The -2 and -6 will give me that -8. So I'm going to put a -2 and a -6 in each of the parentheses. So I have it factored, set equal to 0. I'm almost done, but I still got a ways to go. I set each factor equal to 0. For the x minus 2 factor, I add 2 to both sides and get 2. For the x plus 6 factor, I add 6 to both sides and get 6. For both of these, if I don't check, I'm going to be in a world of hurt because I could write or lose some points anyways. So I'm going to check the 2. I'll go to the original problem and see if the square root of 2 times 2 minus 3 equals 2 minus 3. So let me check that real quickly. Left-hand side, square root of 2 times 2 minus 3 equals the positive 1. Right-hand side, 2 minus 3 equals negative 1. X equals 2 doesn't check. So when I write my answer, either I need to not include the 2 or say the 2 doesn't check. It doesn't matter which. I usually just wouldn't include an answer that doesn't check. But 2 is not an answer to this because it doesn't check. If I did the same thing with the 6, go to the original problem and go square root of 2 times 6 minus 3. See if that equals the 6 minus 3. So left-hand side, square root of 2 times 6 minus 3. Left-hand side comes out to be 3. Right-hand side, 6 minus 3. Right-hand side also comes out to be 3. Because the left and the right-hand side come out to be the same, 6 is the solution. So when I go to write my answer to this problem, I've got some flexibility. So for 29, which is the last problem on the review, my answer, I have options. The best option is just to say x equal to 6. Or, if I want to, I can say x equal to 6, x equal to 2 does not check. So, if you want to include both the answers that the algebra produced, you have to emphasize that one of the answers, even though the algebra gave it to me, it's not an answer that checks. If you wrote x equals 6 and x equal to 2 and didn't make a comment about the 2 not checking, then you're going to lose points because you're saying something's an answer that's not an answer. The algebra produced it, but it doesn't check. And sometimes algebra does that. You can do perfect algebra, but it gives you every answer that does check, but sometimes it gives you extra answers that don't check. So, if you could do everything on this review, you should be absolutely perfect for the second half of the test over Chapter 4. If you've got holes and you're not feeling good about this, always have plenty of time. You can sit down with me and we can work the review one-on-one. I could sit with you and make you some extra problems up. If you don't feel like you have had enough practice on a certain kind of problem, I could usually make up problems pretty quickly, and so I can give you extra problems to practice if you don't feel like you're prepared for the test, because I don't want you going into the test not feeling completely prepared. Hopefully you go into the test thinking you know how to do everything, and if you miss some points, they're just kind of silly, careless errors that I make all the time myself, and not just you're not staring at a problem, you just don't know what to do. That's the bad kind of mistake. Adding 2 and 3 and getting 6, or doing 7 minus 4 and doing something and getting like 28 or something silly. That just happens. You can't really escape that. But big gaps in looking at a problem and not knowing what to do, that's what we want to avoid the best we can. All right, that's got to be good for this.